Hello, everybody. Today we're going to be talking about the principles of stability and why structures fail. So, we have an idea of balance and gravity and what makes a structure stable. But if we're going to construct an actual structure, what are some of the big kind of key concepts that we need to keep in mind when we're going to do so? So, the principles of stability and why structures fail. Principle number one is that you want to build on a firm foundation. Now, I know that sounds obvious, but that's kind of the basic of a structure. If the foundation that you're building on is no good, you're not going to have a very stable structure. So that's principle number one. But, there's several different methods to do this. First method is obvious. Find something solid. Find a solid place to build your structure. So, but what is a solid place to build a structure? How could we do that? Well, we could find firm clay or soil. So firm, packed soil is an okay thing to build on for, say, maybe a house or maybe a bungalow or maybe like a shed or something like that. If we want to, the most stable thing we can build on our planet is bedrock, the tectonic plates of our planet. Everything else is stacked up upon that, the crust of the earth. So we could dig to bedrock. We could just dig down to the bedrock and build right on there. A house doesn't need that. I don't even think apartment buildings need that. But a skyscraper would. A skyscraper would need bedrock. Or we can use pilings. And I'll explain what those are in just a second. So we could dig to bedrock. Oh, sorry, not that bedrock. This bedrock here. And as we can see, we have kind of our layers of soil here. It gets more packed. And then we have our bedrock here. Let me get my pointer up. We have our bedrock here. And this is solid stuff. You can't build on anything more stable than that. We could kind of take off that top squishy layer of soil and build on the clay underneath. The clay in our area, in kind of southern, the soil in our area is very clayey. If you ever had to dig into your backyard for a project, it's a pain in the butt around here. But it's nice and firm to build on. Now, the other thing we have are called pilings. So these are pilings. So they could either be concrete or metal, or sometimes even wood is used. And if you can't dig to bedrock, you can kind of put these down onto the bedrock and then build on top of the pilings there. And then that force is holding onto that without actually putting the foundation on the bedrock. Because sometimes the bedrock is under like huge, hundreds of meters of soil. Like there's lots of dead things that have decayed and piled up on top of that bedrock after a couple, 100 million years. So you may recognize the word piling from the wrestling move, the pile driver. This is technically the tombstone, but it's actually a pile driver. And look, here's how it works. You take your opponent, treat them like a pile, and then drive them into the ground. And that's why this move is called the pile driver. If we were in class, I would demonstrate this on a student now so you fully understand what a pile driver actually is. But here's a real pile driver in action. They load the piling in here, and they kind of use this pneumatic hammer just to kind of go up and slowly, boom, boom, drive it into the ground. It is loud if it's metal, and it takes a good long time because only moving maybe 5 centimeters each time. If you've got to go down a couple hundred meters, that's a long way to go. So principle number one, build on a firm foundation. The first way you want to do that is just find something solid. Find a solid place to build on. Now, another method you could use for this is to simply make a solid layer. I want to build here, but there's nothing solid to build on. So you could make a solid layer. How could you do that? Well, you could pack the soil, you could put down gravel, or you could pour a concrete pad. So you could actually make something there. And this is usually good enough for most of the structures that we have happening that aren't super giant high rises or need to be ultra stable or anything like that. So we have soil here, but we can pack it down so it's much more compact. The particles are much denser together, so when you step on it, it's much more firm. It'll hold that energy. You won't sink in. Think of when you walked through a garden around your house and your parents are yelling at you, how soft and squishy that soil was, because it's not compacted. And we have tools that'll help us do that here. So this is a tool. Look at that. They're compacting that in. No, that's not a Star Wars droid. They're just kind of pounding it down, making it firm, taking out all those spaces so it'll hold that load better. Pouring a concrete pad, very simple. Putting down gravel, again, very simple. And often on top of that gravel, you want to put sand, because the sand will then go in between all the particles and allow for a much more even distribution of the force as well. So that's method number two. Make a solid layer. And then method number three You want to spread the load. This is the most interesting one because the first two are kind of, you could probably come up with very easily on your own. But instead of having all the force go down to one spot, we could spread it out. So, how do we spread the load when we're building on a firm foundation? We can make the foundation thicker than the walls and use many shallow pilings. Let me explain. So here we have a wall coming down here to this foundation, and look at that foundation there. See how it kind of like spreads over? It'll spread the load. So instead of the load coming down right in this one spot, it's kind of a bigger area that's being compressed. And you can kind of think of this if you've ever kind of like, don't you hate it when you're walking across grass in high heels and the high heel keeps sticking into the ground? That's the worst. I hate that. And so the reason being is all of your force, all of your weight is down to that tiny little point. If you're wearing flats or have a bigger heel, that doesn't happen because the load is being spread. And this is the reason why you don't die when you go on a bed of nails. I'm sure some of you have done the bed of nails at the museum in downtown Kitchener. And, you got stabbed by 1,000 nails. Well, why aren't you dead? Well, because each one of those nails held a little bit of the weight. If you asked a young child and said, would you want to rely on 1,000 nails or just one nail? They'd be like, oh, I don't want 1,000 nails, just one nail. But think of all your force on one nail as compared to a whole bunch. It just holds it. There's no magic involved in that at all. So that's what we mean by spreading the load here. But what about this idea of using many shallow piles? Well, instead of going down to the bedrock, which may be way too deep, we can set many shallow piles here to the higher density soil that's been packed a whole lot more. And it'll support it. Not one pile would support all of this, but if we have a little bit of load being bore by each of those, then we can spread the load across those. So that's principle number 1, build on firm foundation. Method number 3, spread the load. Now let's look at principle number 2. We want to balance forces. You want a structure to be balanced. How do we build a balanced structure? Well, we make it reasonably symmetrical. Think about a lot of buildings. They're symmetrical because they will spread the load evenly down there. If we can't do something that's symmetrical, we can use counterweights, or we can use guy wires, not guide wires, guy wires. So think of the CN Tower. Think of the Eiffel Tower, right? They're very symmetrical structures. They spread the load very evenly here. They don't lean too much to one side. Think of a tower crane. Now, a tower crane, here's the base of a tower crane, not very big. And look at the load, look at the weight way out there, right? But look at the weight on the back. The counterbalance will bring the center of gravity closer to the base. In the exact same way when you did the balance challenges, when you bent over to touch your toes, you couldn't do that when you're against the wall because your butt wouldn't be able to stick out. You couldn't deploy your counterbalance to bring your center of gravity back. So we have that counterbalance on the back of that. Guy wires are another one. If you have a structure that's really tall with a really narrow base here, this is a radio tower here. Look at all the guy wires coming off of that to kind of hold it and make it stable and balance it. Really what these are doing are kind of like spreading out the base, making the base of this thing huge because the wires go so far and adding support at the top. We don't need support at the top on the structures over here because they have such a wide base and it's such a rigid and strong material. A lot of people are confused by the CN Tower. How can it be so tall with such a small base? The CN Tower is actually connected to a gigantic block of concrete underneath it that helps it to be stable. That's its base. We don't see the base of the CN Tower. And you know guy wires quite well. Those are things that kind of come off telephone poles here with the big yellow plastic protective things, so you don't clothesline yourself as you're biking by. You can see them very clearly. So those are holding. There's one right at the corner on Laurentian when you're crossing the street there. So that's principle number 2: balance forces. Principle number 3: you want to keep forces vertical. Now this is the most complex. Now we're really starting to get into some engineering here. Method: get the force to the foundation as efficiently as possible. So you want to get the forces down to the ground as fast as you can. How can we do that? Well, we can use a truss structure or an arch. Here, this is what we call a beam bridge. So what's supporting this beam bridge is these, pillars here, and they're in compression. And if you were to stand here on this, your weight would have to travel very horizontally before it can get the support it needs. It has to travel horizontally this way. It's a long way. And that's why things like this, will bend and be in tension and compression as you get that force on them, right? Now, not to say a beam bridge doesn't work, but if you're looking to span a very long distance, a beam bridge isn't going to work because you're not keeping forces vertical. They're running horizontal for a great distance before they can get vertical. This is where the idea of why a triangle is so strong, because it does a very good job of keeping forces vertical. We can't have it go straight down, which would be ideal, but it's keeping the forces much more vertical here. And that's why a triangle is much stronger than, say, a square or a rectangle, because the force along the top of a square or a rectangle would have to run horizontally before it runs vertically. Now, how do we apply this in structures? Well, here's a truss. This is what you call a truss, and this is in a house, and there's truss bridges and all sorts of things like that. So when we have the load on the house, so snow or whatever it might be, we have it can come. If these supports weren't there, it would have to come, vertically there, and then run horizontally all the way over to there to get down. But these will help spread the load out across and allow that force to get there faster. Because if it was a force on here, it'd have to travel horizontally, vertically, then horizontally, or horizontally, then vertically. It'd have to travel all at different distance in different ways. So this allows the force to get there much, much more efficiently and spreads that, so helps spread that load out as well by keeping forces vertical. So these are trusses. And then we have an arch. This is an arch here, and I'm sure you've seen them before, but similar to the trusses, when the force comes down, it spreads it out in a much more vertical fashion. It doesn't have to go horizontally and then down. It immediately starts to move it down. An arch is a very, very strong structure. So that's principle number 3, keep forces vertical, up and down, get them to the ground as fast as possible. So those are the principles of stability, how we can kind of build things to do that. We have 3 primary principles. Now, when we violate these 3 primary principles, or don't pay as close attention as we should, we have a structure that might fail. And we're going to talk about the primary reasons why structures fail. These are kind of very broad 6 categories here, and oftentimes it's a combination of these things that actually cause a structure to fail. But these are the ones we're gonna kind of focus on here. So why might a structure fail? Well, if it has an excessive load, you might say, well, there's too much weight, or you kick it too hard, or a tornado hits it. Those are all excessive live loads. That's really what is happening here. When you have too much weight on a structure and it fails. I went through a lot of the pandas failing gifs to find that one. It was just right. Or it could be unbalanced. So if a structure becomes unbalanced, the center of gravity is not over the base properly, or it's not properly counterbalanced, or the guy wires break, it would become unbalanced and then it would fail. The most famous example is the Leaning Tower of Pisa. They did not build on a firm foundation with the Leaning Tower of Pisa. They thought they were, but they had a foot of clay, but underneath all that was sand. And as they stacked up the big heavy blocks, compression occurred and it squashed that down and began to lean. So the center of gravity is kind of over here on it. It's starting to kind of lean out there. And now you can combine those, like an excessive load. You put too many people on one side of a boat, it will become unbalanced and fall over. And then we have a foundation failure. So that foundation begins to crack. It's not quite right there for it. The foundation washes away. So if the base of it goes, that structure is going to come down. And we also have erosion or fatigue. So fatigue, use your French here, fatigue means to be tired, right? These shoes are fatigued. They are worn down. That's where your toe rubs. That's where your heel rubs. So those things kind of wear down. And buildings and structures and building materials wear down over time. And they have to be replaced. So think about even the wings on an airplane. Whenever it lands, they're extensively checked, every pop rivet, all those sorts of things, because that's a lot of stress and fatigue on there. And then we have erosion. So this is rust, erosion, or corrosion. We have some rust kind of eating away at a pole here, or running water. Water running over a rock will wear it down. You have, if you build by a stream and the stream is running by the base of your house, all that water might wash away the foundation. Then it will have a foundation failure, which will cause it to become unbalanced and fail. See, you can combine these together. Triple failure. We also have bad design. This is one thing that not a lot of people think of a lot of the times. Just if you planned it poorly, or whoever was designing it wasn't trained or skilled or made a major error in that. So, like, very poor design here. That's not going to work so well. Or here's an example of a failure due to bad design. Oh, yeah, that might not be the best thing to use as a permanent foundation there. And I know at the University of Waterloo, they take this kind of very seriously in the engineering program. And because, like, people's lives are at risk if you get these calculations wrong as an engineer, right? So there's a lot of you have to take that job very seriously because your poor design could lead to, whatever, crummy staircase, or it could lead to an entire building collapse because you didn't calculate something correctly. And then finally, we have faulty construction. So let's say your design was perfect, but then you go to build it and you didn't build it so well. Have you ever built something from IKEA or a piece of furniture that you ordered and you have like, look at this, I have 18 extra pieces? No, you don't. You just built it poorly. So here's someone laying brick, and that's not a very good job. So the question is, why would you hire someone who is unskilled to do that job? Well, it's cheaper, right? You want to save money. Hey, I'm a big fan of saving money, but if you're hiring unskilled labor, then that means you're not going to get the job done properly, most likely. And then also, yeah, it sucks paying a lot of money to get a good job done right, but then you've paid that person a lot of money, which is a good thing for that person. So then they can provide things for their family. They can, not live in poverty and things like that. So there's nothing wrong with paying someone well to do a job well. So these are why structures fail. As I said, you can combine these together too. And so make sure that you go through this thoroughly. We're going to apply your knowledge in the next one and see some pretty crazy, just absolutely crazy structure fails. All right, thanks.